In my previous video on Laplace transform, I had ended the video with two questions. That is, as you can see on your at the bottom of your screen, the Laplace transform of t sine of at and t squared cosine of at. So we'll try those two numericals and we'll proceed further into the various other aspects of the Laplace transform. First up, with the questions, let's try them. Well, the first bit, that is the Laplace transform of t times of sine at. So the Laplace transform of t times of sine at is nothing but equal to the Laplace transform of t times of, we can expand sine at as we have it as e raised to the power iat, that is the exponential, minus e raised to the power minus iat entirely divided by 2i, and then we have 1 over 2i can be taken outside, and we have the Laplace transform of so this is multiplied to, so we have the Laplace transform of t times of e raised to the power iat, and minus the Laplace transform of t e to the power minus iat. With that, we can apply the first shifting theorem that we studied. If you remember, let me go back to that page. So this is the first shifting theorem where we have e to the power at, the Laplace transform of e to the power at, f of t is equal to f of s minus a. So here we have f of t as t and e raised to the power iat over there. So that is now equal to 1 over 2i times of 1 over, now instead of simply at, we have iat in the power of e, so we'll be taking the ia instead of the simple a. So s minus ia, this would have been simply s minus a whole squared for the t function, and 1 over s plus ia, that is minus of minus, so that is there. Now 1 over 2i, we simply have to just solve it, and what do we get? We have at the top, we can expand this, so taking the LCM, we have s square plus a square whole squared, the denominator term after taking the LCM, and at the top we have s square plus 2ias minus a squared, and then minus s squared minus 2ias times of minus a squared. With all of that, solving this would give us 2as over s squared plus a squared whole squared. Now we move over to the next question, where we have Laplace transform of t square cosine at. Now because it is t squared, so the 2 factorial term is going to come up in the numerator. So because we know that t raised to the power n is n factorial over s minus a times of n plus 1, that is the Laplace transform of t raised to the power n. But we have a cosine function, which means we'll be expressing it in terms of the sum of the exponential as follows, just like we did in the sine function over there. So we have L, that is the Laplace transform of t square times of, instead of the cosine at, we'll have e raised to the power iat plus e raised to the power minus iat over 2, and that is multiplied to t square. We'll keep the dot over here just to be specific. So that's the solution for the cosine t square cosine at. Now we'll be proceeding with the Laplace transform, the other aspects of Laplace transform, and to start with, we'll be dealing with the Laplace transform of derivatives. So the Laplace transform of the derivative of f of t. We'll be doing the integration thereafter. So the Laplace transform of derivative gives us the f prime t, which is the first order derivative, and that the formula for that is simply s times of L, that is the Laplace transform of f of t minus f of 0. The Laplace transform of f of t obviously is capital Fs, as we had written in the previous as I had given the definition. By definition, we have the Laplace transform of f of t to be given as simply Fs, capital F, function of s, and we can have the proof of it in case you need it. So let me just prove it uh, for having a surety test. So this is Laplace transform of the derivative, and that is equal to e raised to the power minus st, because we'll be integrating this in by parts. So we'll be taking e raised to the power minus st as the second function and f of t as the first function. So an integration of that will give us f of t itself minus the derivative of the second function. This is, remember, in integration by parts. So this is minus s e raised to the power minus st times of the given function, the integration, first integration of it, and then that is integrated over entirely 0 to infinity. So this leaves us with a minus of f of 0, because the infinite term, the exponential term with the infinity, the negative power is going to go to 0. So we'll be left with only the 0 term. So e raised to the power 0 in that case is 1, and f of 0 is what we get. And then we'll have over here, because of the minus of minus, we'll have a plus over there, and 0 to infinity, the integration of e raised to the power minus st f of t dt, and this is nothing but what we have as the Laplace transform of f of s. Oh, I forgot the s over there, so that's the s that is multiplied outside, that has come outside. So finally this is nothing but the Laplace transform of f of t. So we have s times of the Laplace transform of f of t minus f of 0 is what we get from the Laplace transform of the first order derivative. Now this is the first order derivative. We will have many such cases where we have higher order derivative terms, and those can be solved as follows, that I'll be providing right now in the next page. Now in case we are looking at the nth order derivative term, then we'll proceed as follows. That is the Laplace transform of this is the nth order derivative of f of t, and that will be equal to s raised to the power n Laplace transform of f of t minus s raised to the power n minus 1, with the powers of s decreasing further, and it continues to Sn minus 2 f of 0, but this will be the first derivative of f of 0, and then we can proceed as follows right up to the nth derivative of not the nth but the n minus 1 th derivative of f, and in that case s raised to the power n minus of n minus 1 is s raised to the power s raised to the power 0, so that doesn't feature, that goes to 1. And we have already proved the first derivative, and this will be proved in a similar manner, because we can prove it. So until unless you require it, I'll probably skip it, because it's going to be a big one, fairly big one than the previous case. So you can use that. Just in case, a hint that you might require to solve it is that the second order derivative, which we'll be probably using quite often. So the Laplace transform of the second order derivative of f is therefore, with respect to what we get over here, can be given as s of the Laplace transform of s times, not of, but s times the Laplace transform of the first derivative of f of t minus f primed 0. And we know that the Laplace transform of the first order derivative is simply, if I expand it, this is simply s times of the Laplace transform of f of t minus f of 0 whole minus f dash, that is the first derivative of f of 0. So multiplying this, what we get is s squared L, that is the Laplace transform of f of t, minus, well, we can keep that, so this is s times of f of 0 minus f dash times of f of 0. So that's the case of Laplace transform with the higher order derivatives. So this is just a hint to allow you or to help you to obtain the value or the proof of the above uh, case. Now with derivatives done and dusted, we can move forward with the Laplace transform of the integral. Now the Laplace transform of the integral of f of t is simply from 0 to t f of t dt is going to be 1 over s times of f of s. You know, f of s is simply equal to the Laplace transform of f of t. So let's prove it if we can. Let's try. So let us take phi t, the function, to be equal to f of t dt taken from 0 to t. And we have phi at 0 to be equal to 0. Then phi prime, which is the first derivative of phi with respect to t, is simply going to be f of t. Now we know that the Laplace transform of phi prime t is going to be s times of the Laplace transform of phi t minus phi of 0. And that will give us s times of the Laplace transform of phi t only, because the second term is equal to 0, which is what we have written over here. And from that we have Laplace transform of phi t to be simply equal to 1 over s times of the Laplace transform of the first order derivative of phi t. Now if we put the values of phi t and phi prime t over there, what we get is Laplace transform of phi t, as we know, is this one, which is equal to the integration from 0 to t f of t dt is equal to 1 over s times of the Laplace transform of, well, what is phi prime t, which is equal to f of t, so that is f of t, which is what we wished to prove, because this is 1 over times of f of s, which is written over here. So that what was to be proved has been obtained. This is the Laplace transform of the integral and corresponds to the division of the Laplace transform of f of t by s. Right. Then next we'll be trying to obtain the Laplace transform of t multiplied to f of t. Now in the first shifting theorem we had an exponential term multiplied to f of t and we obtained the Laplace transform of that, but in this case we'll have t multiplied to it. We'll rather take a generalized case of t raised to the power n times of f of t. So if we are to obtain the Laplace transform of t raised to the power n times of f of t, then that would be equal to minus 1 raised to the power n, the nth order derivative with respect to s of f of s. And you know what is f of s. F of s is simply the Laplace transform of f of t. So that is what we have when t raised to the power n is multiplied to f of t. We can prove this. For proving that, we'll proceed to the next page. So the Laplace transform, as we know, of f of t is equal to f of s, which is from 0 to infinity e raised to the power minus st f of t dt. That's okay. Now if we differentiate this thing with respect to s, so that means differentiation of f of s, which is the Laplace transform of f of t, with respect to s, that is going to give us d over ds times of this integration term e raised to the power minus st f of t dt. We can take that integration inside, so we have 0 from infinity, the partial derivative with respect to s of e raised to the power minus st f of t dt. Now we take the derivative with respect to s of the exponential term, so we have minus t e raised to the power minus st f of t dt, and if we take that minus t and multiply it to f of t, so we have the integration from 0 to infinity. We can take the minus sign outside for now. We'll have e raised to the power minus st t times of f of t dt, and if you observe closely, this is simply the negative of the Laplace transform of t times of f of t, because that's whatever is over here multiplied to e raised to the power minus st, that is simply the Laplace transform of that. And this is nothing but the derivative d over ds of f of s. Now we can take the minus sign onto this side, and we can take that minus sign as minus 1 raised to the power 1. Similarly, if we take the second order derivatives, that means we are considering Laplace transform of t square times of f of t. So in that case, it will be minus 1 raised to the power 2 times of the second order derivative of f of s with respect to s. And similarly, if we proceed likewise, we'll get the Laplace transform of t raised to the power n f of t is equal to minus 1 raised to the power n dn over ds raised to the power n f of s. That is the proof of the Laplace transform when t raised to the power n is multiplied to f of t. So that's more or less the case over here. We can try a few numericals related to this, which is what we'll be discussing in the next part or the next video in this series. Till then, thank you for watching.